put text on there to fix stuff, and then it's obviously takes me a while to put the text in there. So that's the holdup. I want to get it out to them within the next like 48 hours or so. Did I actually hit record? Yeah. All right, so surface heat capacity is based on thermal capacity. It is the energy required to raise the temperature of a unit area of a plant. Right, so it has nothing to do with mass, but it's the thermal capacity per unit area. Right, so the energy required to raise the unit area of a planet's surface temperature by 1 degree. 1 degree Celsius, 1 degree Kelvin, whatever. This is in your data booklet. Can you please find it so we can make sure that it looks the same and we can agree what all those symbols mean? It looks to me like it's pretty much identical to this. So the capital C subscript S is our surface heat capacity. Q would be the energy, right? A is our surface area term, and then delta T is our change in temperature. Right, so it's actually the same definition as thermal capacity, except we have this area term built in. So the unit that surface heat capacity would be measured in would be the unit of heat, which is joules, divided by the unit of area, which is meters squared, and the unit of temperature change, which would be Kelvin. All right, questions from anybody about this definition of the surface heat capacity? It's implied that that's for a planet. I suppose it would be the same thing for a moon, if we really care about planets.
I don't know if we could.
Bloody nose? Yeah. All right, so again, this just comes from our thermal capacity expression. So what we're going to do with that today is incorporate it into what's called an energy balance climate model. So an energy balance climate model is pretty darn simple. All right, who's that? Why isn't it the Earth? What?
Ultraviolet.
That could be. What?
It's not hot enough.
It is supposed to be the sun, but it equally could be the Earth, right? Because the Earth emits rays as well. They're just infrared mostly, not visible, and ultraviolet mostly. Yeah, so that's the sun. And then here's the Earth, right? So we have power coming in from the sun. Maybe it'll show the atmosphere to you. So we have power coming in from the sun, and how much of that counts? 70% counts. Right? The albedo is 0.3, so 30% of what's coming in from the sun actually does not get involved with any potential temperature change. So 70% of that counts, but then we are radiating power away as well. So if the energy in or the power in and the power out are exactly the same, then our temperature should stay constant. Right? We have a power or an energy balance. And if that happens, the change in temperature should be zero. I mean, we'll have weather, but the average surface temperature of the Earth should stay constant. If we had more power coming in and less power going out, what's going to happen to average surface temperature? It's going to go up, right? If we have more power coming in and we're releasing less power, the temperature is going to go up. But if somehow we emit more power than we receive, our temperature should go down. So that's what an energy balance climate model looks at. It just looks at how much energy is coming in, how much energy is going out, and then what can the surface materials do with that power imbalance. Right? That's our surface heat capacity term. Alright, so I don't want to talk for too much longer. But our whole equation built into our climate model today is just our surface heat capacity expression, right? We are concerned about temperature changes today. That's what we're going to be tracking as we alter some things. So I've just rearranged our surface heat capacity expression for a change in temperature, right? Our Q would be related to how much power is coming in versus how much power is going out, right? In fact, power is the rate at which an energy is converted, right? So I'm just substituting in energy or a change in energy for power multiplied by time. In this instance, it's the thermal energy that we care about. So the only thing I've done is manipulated to solve for change in temperature, and then stuck in power multiplied by time for the heat. All right? All right, fantastic. Now, we're actually not going to be getting amounts of radiative power. We're going to be using this intensity that we first talked about, I don't know, a couple of classes ago. So the intensity of the solar radiation is what we're going to care about. And notice that that has power and area in it, right? So I can substitute in a single term, intensity, for these two terms that show up in our surface heat capacity expression. And this is the equation that we're using in our model. So our change in temperature is solely based on three things. The intensity of the sun's, it's the intensity of the sun's power, but minus the intensity of the Earth's outgoing power. The amount of time that we're letting the model run for, and then the surface heat capacity of the Earth. All right, so if the incoming intensity is the same as the outgoing intensity, then the net power is zero, the net intensity would be zero, so the change in temperature, the delta D, should be zero. Right? Again, the I would be the net intensity, so we have to subtract what the Earth sends out from what the sun sends to us. If that term is zero, we get no temperature change. All right, so that's pretty much all that I want to say about what's built into the model. Let me show you the model itself, and then tell you what you're gonna do and what you're gonna turn. So I emailed you two files. The one file is just like instructions. It would help if I had the right here. The one file is just a PDF that has instructions. And so there's like 5 pages. Mixed into these 5 pages, there are some questions. So you're gonna just open a Word document, or you can just do what do you call it, a Google conversion of a Word document? A Google, yeah, okay. Whatever you do a Word document or do it right into Google, you're gonna ultimately, if you do a Word document, you're gonna upload it into Google anyway. So anytime there's a question, just go ahead and answer that question, right? So write question 1, go ahead and submit your answers. Here we have some assumptions of the model that we're supposed to read about. So the rate of the incoming radiation from the sun, we're just fixing it at 364 watts per meter squared, right? And then the outgoing radiation of the Earth is the Earth's radiative power given by the Stefan-Boltzmann equation, right? So if we care about the outgoing intensity, we don't have to worry about the surface area term because that's built into the intensity. So all you have to do is multiply the Stefan-Boltzmann constant by the Kelvin temperature of the Earth's surface raised to the 4th power. Right? We have another question built in. We have a little more information about the model, which is what I already showed you. Another question, and then we're given some instructions on how to operate the model. So the model is just an Excel spreadsheet. Let me zoom in a little bit so we can see stuff better. Okay. So we have some values in this top row of cells. So the 5.67 times 10 to the negative 8. Turn the lights out so you can see that better. It's just our Stefan-Boltzmann constant. And if you kind of hover the little selector tool on top of it, it tells you that it's the Stefan-Boltzmann constant. We have the surface heat capacity of the Earth right here, so that's built into the model. And then we have the time increment that we're going to operate our model off of. So this is the number of seconds. In this case, it's the number of seconds in a half a year, I think. Yeah. No. Yes, it's the number of seconds in a half a year. And then we have 5 columns, which are essentially our model. So we have a column for the number of years that have passed. We have a column for the incoming radiation. So initially that's set at 364. We have a column for outgoing radiation, which is what we get from using the Stefan-Boltzmann equation. We have a column for the temperature change, and we have a column for the actual average surface temperature of the Earth. Now, the first thing that we do in this model is increase the incoming radiation by 5%. That's already done for you when you open the model, right? So this first cell just increases the solar radiation by 5%. And then we want to model what that does to the surface temperature of the Earth. So what I'm going to do is highlight that row of cells, and then I'm going to drag the little box on the lower right-hand corner down, and that will fill those formulas in to all of those cells, right? So after a half of a year, well, we're doing a one-time 5% increase in the sun's radiation, so that's why this stays constant at like 382 watts per meter squared. But the Earth's radiative power output increases as the temperature increases. So that's not staying constant. The temperature change should decrease as time goes on, because as the radiative power output increases, right, we get closer and closer to emitting what we're getting from the sun. So eventually we get no temperature change. Eventually we'll reach an equilibrium temperature, and that's what we want to use this model to do, right? So that's essentially what you're going to be doing for the rest of today. I'm certainly happy to help you if you run into problems, but we're just going to vary some of those things to see what effect it has on the Earth's temperature. Now, so let me cut back to the PowerPoint at this stage. I'm not going to go through the questions that you're answering in your document. We already talked about some of the assumptions in the model. So what you'll be doing, and then hopefully finishing this period, I'm suggesting a Microsoft Word document to answer questions and display the graphs that you make. You'll be making graphs of temperature as a function of time. I want those graphs embedded in your Word document, right? So put them in sequence, like with the stuff that you're answering. Each time that you change the model, you should be making a graph. Now I just got back to the thing. So every time you make a graph, you need to put that into your document, and then ultimately when you finish, you're going to upload that Microsoft Word document into your Google Drive and then share it with me. If I do have jury duty, I plan on reading the stuff, and if I have it electronically, that'll make my life easier. So at this point, if you don't already have a computer in front of you, you can go ahead and sign one out. If you neglected to put this on a flash drive, I did put the two documents on a flash drive. Please ask me if you run into something that doesn't seem right. So you do have the whole period to work on this. It is my hope that that'll be enough time to finish. Yes, it is on all three of those 5 drives.
What's your biggest